In this video, we're going to look at friction and equilibrium in the case of a mass on an inclined plane. Alright, so here's a situation of equilibrium where all the forces are in balance so that the net force on the object is zero. So that's our situation. This is a given. This block is subject to zero force. Its net force is acting on it as zero. The net forces, that is, there are plenty of forces acting, as we'll see shortly, but the sum of all those forces in each of the perpendicular directions is zero. Two-dimensional problem, so we should have two orthogonal directions. That's the I and J direction. So we'll choose plus I to be to the right and vertically up to be positive. So positive J direction, positive I direction. Okay. So here's the mass. We imagine all of its mass is located at its geometric center and all the forces act through that geometric center. Okay, so we have a mass sitting on a plane here, inclined at 30 degrees. The weight force is acting downwards towards the center of the body on which, whatever body within the universe that this is on, the Earth or some other planet or some other star or galaxy or what have you. Okay, G is acceleration due to gravity for the body it's on. And here's our block sitting here, the weight force vertically down on the page. Making an angle with the J direction here, I might add. The friction force acts up the plane because it acts against the block falling down. Okay, so we've got a particle of mass 5 kilograms rests in equilibrium on a rough plane inclined at 30 degrees. Find the maximum value of mu. Okay, remember the frictional force is mu times the reaction force, and we want to find the value of mu. Now the friction is such that it acts up the plane, preventing the block from driving down. Gravity wants to pull, as has a component of gravity, is pulling it down the plane. We'll talk about that shortly. In the I direction, we have plus friction force acting in the positive direction, so plus Fr, and we have here a component, the sine component. This is 30 degrees in here. This component here is 5g sine 30 degrees, so 5g sine 30 degrees, that's this component here. Okay, 5g sine 30 degrees. Friction force minus 5g minus this part of the weight force, this component of the weight force, sums to zero. Okay, so that tells the friction force is equal to 5g sine 30 degrees. All right. Now, that's the I direction. All the forces sum there to zero. So here's our first equation. Let's have a look in the J direction now. We have plus R coming out of the plane. All right, and we have this component of the weight force. Here, this is the cos component. Okay, and that's going to be 5g cos 30 degrees. 30 degrees is the angle in there. Okay, and so R plus R, because it's in the positive direction, 5g cos 30 is in a negative direction, so minus in front, so R minus 5g cos 30 degrees must also sum to zero because this is an equilibrium. In an equilibrium situation, the net force in each of the orthogonal directions that make up the two directions of this two-dimensional problem must sum to zero. Okay, so we've got R is 5g cos 30 degrees. All right, now we know that the friction force, Fr, is mu times R. Okay, well, what we have then is that mu is the friction force divided by the reaction force. And we have expressions for both of those. For the friction force, we have 5g sine 30 degrees. For the reaction force, 5g cos 30 degrees. Now, as you can see, the 5g's cancel out. And mu, the coefficient of friction, is the sine 30 degrees divided by the cos 30 degrees. Okay, which is just tan 30 degrees. Tan 30 degrees by the exact ratios is 1 on square root 3, which is approximately 0.58. So your coefficient of friction is 0.58. All right, that's not the only way we could have worked it out. Given in the last couple of videos, we've looked at Lami's theorem. We could have used the reaction force divided by sine 120 is equal to the friction force divided by sine 150 is equal to 5g, the weight force, divided by sine 90 degrees. You remember in that particular, and F, the friction force is mu times R. And then for that, if you remember, okay, the weight force divided by the sine 90 degrees, reaction force divided by sine 120 degrees, friction force divided by, what was that, sine 150 degrees. Okay, remember that from the previous videos? Okay, now in general, mu is given by tan theta is Fr, the friction force on the reaction force, or mu R on R, or mu. Okay, so mu is equal to tan theta. If you know the angle of inclination, just put it in there. Tan of that angle will give you the coefficient of friction. This can give us the angle of the inclination of the plane, i.e. the limiting value of friction. That's the point beyond which the frictional force can no longer hold the object and equilibrium is lost. Motion begins to occur. All right, that's that.